Hello and welcome everyone. So we are discussing free damped vibration in which damping is present, and damping is due to the dampers and the dashpot. And due to that, there is one more additional component of force added in the equation of motion, that is damping force Fd. And Fd is proportional to the velocity, because Fd force, damping force, is trying to resist the motion of the body, and this Fd is equal to c times velocity of the body, where c is the damping coefficient. Okay, and if we assume the solution of equation of motion x is equal to e to the power lambda t, and we substitute this value of x dot and x double dot in the equation of motion, then we arrive to a characteristic equation, and characteristic equation is a quadratic equation of lambda. And it is said as characteristic equation because it characterizes the type of motion the body will undergo, and it depends when we do the solution for the lambda 1 and lambda 2, we come to this value of d is equal to c square minus 4 km. Now the nature of d will decide the nature of damping. See, if d value becomes greater than 0, that means there will be real solutions, and that is overdamped system. Okay, overdamped. And if d value comes out to be negative, that means less than 0, solutions will be imaginary in the form of complex conjugates, and of course it will be called as underdamped systems. And if by chance we get d value equal to 0 exactly, then that is the situation in which there is critical damped system. Okay, there is critical damping happening. Okay, and we have discussed this third category, critical damping, because it is very easy to understand, and we have seen in this we have defined a parameter also, damping ratio zeta or rho is equal to c by cc. Okay, this is a ratio of damping coefficient and critical damping coefficient. So critical damping may be defined as the minimum amount of damping in which the system will not oscillate at all. Okay, even if we disturb it initially, it will simply come back to its original position or the equilibrium position after one natural time period. Okay, so this is a non-periodic motion. Okay, you can see from the graph also. So if we increase damping, then of course that will come in the category of overdamping. Okay, so of course in overdamping there is no possibility of periodic motion. It will not allow to oscillate. Okay, because damping is more than the critical damping. Okay, so now we are going to discuss today about the overdamped systems and underdamped systems in detail. So let us start. And as we have discussed, the damping ratio, which is the ratio of damping coefficient C divided by critical damping coefficient Cc, is the damping ratio represented by rho. And if C value is equal to Cc, then rho will be equal to 1, and that is critical damping situation. But now we are increasing the damping coefficient C value greater than critical damping, then it will become greater than 1. Okay, so this is the situation when there is overdamping. Okay, and in an overdamped system, the d value discriminant will become greater than 0, that is c square minus 4 km. Okay, so here we are going to get real roots and real and distinct roots. Okay, so if we assume alpha and beta are the roots, they are going to be real and distinct, and we can solve the distinct values of alpha and beta from this equation, and this equation is simply derived from the quadratic equation. Nothing to remember. Okay, this is not to be remembered. Now if we do some rearrangement by multiplying and dividing by the same value omega n in the numerator and denominator, equation will remain unchanged. All right, and here we have done the same thing. Okay, what we want to do, actually we want to convert this situation in terms of damping ratio. Okay, we want to convert in the form of damping ratio. Okay, so same thing is done here. Omega n is taken as outside in constant, and rest thing will follow. and then we have written it in the form of 2m omega n. We see that 2m omega n is coming here in the denominator and here also. So both of these terms, we know that 2m omega n is equal to what? C, critical damping coefficient. How? Critical damping coefficient we have calculated the Cc here, and it is the situation when rho value was equal to 1. Okay, and C here D is equal to 0. When we put D equal to 0, we get the value of Cc, and Cc is critical damping coefficient, that is a constant. Okay, it depends simply on its natural angular velocity and mass. So Cc is constant. So we have written it in the terms of C by Cc here, and here plus minus root under C by Cc ka whole square minus 1. And we know that rho value is equal to what? Damping ratio is the ratio of C by Cc. So we have now written the equation, this entire equation in terms of damping ratio, just simply by multiplying omega n and in the numerator and dividing by omega n, by putting it, multiplying it in denominator. So this is the equation. Alpha and beta is equal to omega n minus rho plus minus root under rho square minus 1. Okay, so this is very simple equation, even you can remember it, the two value here. Okay, so we know that a rho value is greater than 1, rho is greater than 1, so rho square is also greater than 1, so this value is going to be positive only. Okay, now let us come to the general solution for an overdamped system. Now we will be very easily calculating C value will be given in the problem, and Cc we can calculate as 2m omega n. This will give us the rho value, and just put this value rho in this equation and we will get the value of alpha and beta distinct. Now let us come to the general solution here, and it says, although we have assumed that x value was equal to e to the power lambda t, but since we have two solution here, for lambda value, lambda 1 is equal to alpha and lambda 2 is equal to beta, so x will not be as simple as e to the power lambda t, but it will become like a times e to the power alpha t plus b times e to the power beta t. Alright, just see this simple transformation, and because we have incorporated both the roots, okay, alpha and beta here both as a general solution, so this is same thing is written here. Here x is equal to e to the power alpha t plus b to the power b into e to the power beta t, and we have put the value of alpha and beta also here. Okay, this is the final equation here, and what we can do here, if something can be taken as common, what can be taken as common, that is e to the power minus rho omega n t into alpha. If we take this as common here, then this alpha is not so big. We have taken e to the power minus rho omega n t, okay, in common, then here in denominator, here it will be remaining here, first of all a into e to the power omega and rho square minus 1 times t plus b into e to the power minus omega n rho square minus 1 under root into t. Okay, so this is what it remains here in the bracket. So if we see, this equation also is in the term of a e to the power minus x types, e to the power minus t. Okay, in the term of e to the power minus t, that is exponential graph. Exponential decay looks like this only. Okay, it's a exponential decaying, so the graph will look like this only. This is the displacement plot of an overdamped system, and if we go on increasing damping for higher damped system, it will slow down very slowly. For slightly overdamped system, it will slow down fastly. Okay, This is how the graph looks like. And of course all these graphs start from some initial position like this. Okay, so the motion of an overdamped system is non-periodic because there is more damping than the critical damping regardless of the initial conditions. And if we go on increasing damping, it will take long time to decay from an initial disturbance. So this is about the overdamped system. And if we talk of the equation of motion in underdamped system, then it is going to be really a wonderful experience when we calculate for an underdamped system. And we know that in underdamped system rho value is less than 1. And here we are going to get complex conjugate roots. Of course there will be two roots, and damping is underdamped, so there will be oscillation here. Okay, so let us start. For an underdamped system, the discriminant is negative, d value is less than 0, and then here CV is also less than CC. Okay, C by CC is less than 1. All right. So thus the roots of the characteristic equation are going to be complex or imaginary, and we can write here simply as we have done in the previous situation that alpha and beta will be same, omega n minus rho plus minus root under rho square minus 1. But here since rho is less than 1, so rho square also is less than 1, so rho square minus 1 is negative. You understand this? So this value is negative, so this will give a imaginary number. Okay, now this is the displacement plot which you are seeing here for the underdamped system, and you can see clearly here the body is oscillating. Okay, and although the amplitude is decreasing with time, but body is oscillating. There is periodic motion here. Okay, so this is the displacement plot of the underdamped system. How it is derived? From the equation of motion. Now the general solution for equation of motion in underdamped system will be equal to x is equal to a into e to the power alpha t plus b into e to the power beta t. Okay, let us put the value of alpha and beta from this equation. Okay, and we can simply replace this equation here. X is equal to a into e to the power, take omega n common here, minus rho plus root under rho square minus 1 times t plus b into e to the power omega n minus rho minus root under rho square minus 1 times t. Okay, so this is the final solution for the equation of motion. Now what rearrangement here can be done? So let us take first of all e to the power minus rho omega n times t as a common component from both of the terms, and write the internal components here as a e to the power omega n into rho square minus 1 times t plus b into e to the power omega n minus sign here rho square minus 1 times t. Okay, now here we know that rho value rho square is less than 1, so rho square minus 1 is negative, so we can write root under rho square minus 1 equal to iota times 1 minus rho square. How this is written? This is written as we can replace if it is our rho square minus 1, what we can do, we can put it as, let's put rho square minus 1 equal to, take minus 1 as common. Okay, here minus 1 we have taken common, and it will be equal to 1 minus rho square, and we know that minus 1 is the square of iota, it is equal to root under iota square 1 minus rho square. So this can be written as iota root under 1 minus rho square. Okay, so when we do this rearrangement, ultimately 1 minus rho square will be a positive term. So this root under will be a real number, but it is multiplied with the iota also. So now we are going to write this equation of motion solution here. So this is the general solution here, written again as x is equal to e to the power minus rho omega n t, which we have taken common already. Now in the bracket a times e to the power iota omega n under root 1 minus rho square times t. Okay, here we have replaced under root rho square minus 1 by iota under root 1 minus rho square. Similarly here also plus b into e to the power minus iota omega n into 1 minus rho square under root multiplied by t. Okay, so this is here done, little arrangement. Okay, so the solution for the underdamped system, it can also be written as x is equal to e to the power minus rho omega n t plus into under bracket a e to the power I omega dt plus b into e to the power minus, here it should be minus iota omega dt. Okay, now what is omega d? Omega d is called as damped natural frequency. Omega d here is called as damped natural frequency. Okay, because of damping, since it is underdamped system or overdamped system, but this component omega d will always be called as damped natural frequency, and omega d is equal to what? Omega d is equal to omega n into 1 minus rho square. Okay, so omega d is generally calculated in the case of underdamped system. Okay, and now you can see we have just changed this equation of motion by using this omega d, and it is changed to a very simple form, isn't it? X is equal to e to the power minus rho omega n t multiplied by a e to the power iota and omega d into t, that's all, plus b into e to the power minus iota omega dt, that's all, where omega d is equal to omega n into root under 1 minus rho square. Okay, now we know that any component, in case of if you have studied complex number, in complex number we say that e to the power iota, let's say theta, then it can be written as sin theta plus iota cos theta. This is the general formula. In case of complex number, e to the power I theta can be expressed as sin theta plus iota cos theta. So this again, this solution is rearranged here, let's say like this. How it is arranged? It is very simple. We have done again the same thing here. Okay, so we have written here x is equal to e to the power minus rho omega n t into a multiplied by cos omega dt. Okay, cos omega, here theta is what? Theta is equal to omega dt. In our case theta is equal to omega dt, so that's why it is written as a into cos omega dt plus b into sin omega dt. Other terms will cancel out each other. Okay, now finally x can be written as, see, there are many generalization and assumptions involved while arriving to a simple equation, as simple as we can. Now any summation like this can be written as sin omega dt plus phi and multiplied by another constant, let's say x, capital X, and you can easily calculate the value of x will be what? X will be equal to root under a square plus b square. Okay, And we have just done simple transformation in trigonometry, as you can write a cos theta plus b sin theta equal to root under a square plus b square into sin theta plus phi in some form. Okay, and phi value can also be derived. It's very easy. So this is how the final equation looks like, as this: x is equal to, small x is equal to capital X into e to the power minus rho omega n t into sine omega d t plus phi. Now in this equation, this is our final equation in case of underdamped system. You can see there are two parts. Let's talk of first of all periodic motion here. The one part we can separate here. This is the multiplication sign, and we can separate this term sine omega dt plus phi. This is a periodic motion. Okay, so underdamped system will be undergoing periodic motion also. But since another term here being multiplied here, it is a exponential decay term. It is in term of e to the power minus rho omega n t. That is a exponential term, and it is this is a minus sign here, so it will be a decaying, okay, exponential decay term. So underdamped system is both exponentially decaying as well as periodic motion. All right. So this sin omega dt plus phi is causing vibration here. All right. The term sin omega dt plus phi causes vibration, and here omega d is damped natural frequency, for which we can calculate damping time period Td also, and Td is equal to we can calculate 2 pi by omega d. Okay, and this is not natural time period, this is damped time period. Okay, that's why we have used here omega d here. You see this 2 pi by omega d, and omega d is equal to what? Omega d is equal to omega n into root under 1 minus rho square. Okay, and here amplitude will be this x into e to the power minus rho omega n t. Okay, so this is an exponential decaying term, and you can easily get the idea that amplitude will be decaying. So we can conclude that the system which is having underdamped system will be vibrating at a what time period? At damped natural frequency or damped time period, which is a function of natural undamped frequency omega n and damping ratio rho. Okay, the natural damped frequency omega d is less than the undamped natural frequency omega n. But for many practical cases, the damping ratio is relatively small, and hence sometimes the difference is very negligible. That means many a times rho is almost equal to 1. Okay, almost equal to 1, and or it can be slightly more than 1 or slightly less than 1. Then in that case, omega d also almost equal to omega n. Okay, but in practical cases we take like this, but in numerical analysis we try to do separate both the things, damped natural frequency and undamped natural frequency. This is omega d is damped natural frequency and omega n is undamped natural frequency. So today we have discussed the equation of motion in both overdamped system and underdamped system. Hope you must have understood them, and we will be discussing few numericals also on damping in the coming videos. Till that, stay tuned and stay safe. Thank you.